So some of you may remember a little while ago, about a year and a half ago, I bought a big pallet of stuff off eBay. Originally it was just going to be the CNC lathe, and the seller said to me, do I want a CNC mill? And I said yes. So he chucked in a load of extra stuff for a bit of extra money. I ended up with enough bits to make a manual X3 mill, which is the one that you saw in the Sieg X3 versus VM25 video, and also enough bits to almost make a CNC mill. Now, I wasn't missing much. It's missing gib strips, so I made some of those out of a few bits of brass that I had lying around, and it didn't have a table, but fortunately I could buy a table from a local supplier. The main issue was the drive electronics. So the drive electronics are very old that were supplied with it, and there was no documentation. I could find no detail on the internet. I could find odd forum posts of people asking similar questions to those that I had. Very little in the way of answers. So I decided to get rid of all of that lot and just replace it with stuff that I knew how it worked, because it was going to take long enough to get this thing working. So I didn't want to spend days, weeks, months trying to reverse engineer some very outdated hardware. So I've put in another gerbil board, or GRBL, same as I've got on the CNC lathe. It's a very basic type of CNC controller, but it works over USB, which is convenient. You can use it with free software, so you don't need to pay subscription or buy a license like you do with, say, Mac 3 as a CNC controller. I use UGS, or Universal G-Code Sender. I generate the G-code that I use in Fusion 360, and that's on the free license. I don't have a paid license. People have asked me that before. The restriction that it puts on you is that it won't do rapid moves in your programs. So whatever your cutting feed is, that's the speed at which the machine will move in between cutting moves, which makes it quite tedious. Obviously they're trying to annoy you to the point where you buy a license. It's also quite good when you're learning CNC to not have a machine that shoots towards the chuck or towards the vise at breakneck speed without you having any idea whether it's going to stop at the right place or not. So I'll get this back together shortly, but I've still got a couple of things to demonstrate before I put it back together. So let's just look at the electronics enclosures. This is the standard X3 back end, which has the brushless motor driver in it and the basic electrical functionality to make the thing work. And then for the CNC, you get this extra box that basically just bolts on the back of this opening with a load of extra stuff. So what I've got in here is, this is a GRBL gerbil controller. This one was about £30 off eBay. It's 4-axis, so I've got X, Y and A in here, and my Z-axis controller is down there. We'll get to that in a minute. These power supplies, which provide the power for the stepper motors to move the machine, those came in the box of stuff that I got with the CNC machine, so that was very useful. They are just generic 48 volt 350 watt power supplies. These stepper drivers, these three at any rate, are again really cheap. It was about £30 for 3 off Amazon for those 3 stepper drivers, but they seem to work really well. This is the old Z-axis stepper driver, so it's a DM556. So all the motors have 5mm pitch lead screws with double ball nuts. A normal stepper motor is 200 steps per revolution, which would only give you 40 steps per millimeter if you were just to drive it straight like that. But these stepper drivers allow you to do a number of different pulses per revolution. So I've got it set to 1,000 pulses per revolution. That means we get 200 pulses per millimeter. So it's effectively able to move to within 5 microns resolution. So overall, this thing is actually working quite well. I had one fairly annoying problem though. It was that I was losing steps on the Z-axis. Now I could drive the Z-axis really fast up and down, so the motor definitely had enough torque, but I found that if I went down and then up, or up and then down to the same position or to the same programmed position, I would have actually lost around about 100 to 150 microns of travel, and it was a little bit variable. Now this thing does come with a gas strut on the side to take some of the weight of the head, and that improves things a little, makes it a bit more predictable, but it severely limits the travel of the head. So this point here and this point here are the original limit switch locations. So that is the entire travel that you've got with the gas strut. Whereas I've now got a micro switch here and a micro switch down here, obviously minus the thickness of this because it touches on the top and it touches on the bottom. But that is more than double the travel, and you've got all this column, so I wanted to open that up. How do you go about fixing this? Probably 3 years ago now, I bought the bits for a Clow 42 electronic lead screw for the lathe, which involved a closed loop stepper motor and an encoder so that you can synchronize the spindle to the lead screw. So this is a perfect application for a closed loop stepper. I'm trying to turn a lead screw, it's not turning quite enough, so if I close the loop, I should hopefully be able to correct for that error. Now the closed loop stepper that I got was a couple of frame sizes smaller than that one down there, so probably not as torquey, but a little bit of experimentation with it meant that I found out that one, I didn't need a fancy motion controller, i.e. the gerbil board isn't really set up for doing anything about problems with the closed loop. Up to a point, a closed loop stepper controller and motor will make up for lost steps autonomously without the need for the motion controller, in this case the gerbil board, to do anything about it. There's no... the gerbil controller has no capability to interact with a closed loop controller. It just says do this many steps and assumes that that's the case. So I needed something that would, take that instruction and then just make sure that that had happened. So it turns out that the stepper motor driver that I bought for my electronic lead screw would do exactly the job that I wanted. So I went about fitting it. Now I could have bought a off-the-shelf closed loop stepper of this frame size, but because it's got an encoder on the back to tell it how many steps it's done, it's another inch longer. So one option was to make riser blocks for this to give me the extra room, but I decided it would be a little bit more interesting to actually mount an encoder at the top of the lead screw, because that would also take out any losses in the coupler here. So what I did was I took apart the encoder that I bought, put the magnet on the end of the lead screw, mount the board above that, and effectively close the loop. So that involved taking the block, the bearing block at the top of the lead screw off. I also need to try and extract the bearing so that I don't fill it full of cast iron dust when I'm machining the top. I don't have a tool to get this out. What I do have is this. We are. I then needed to bore it out to allow the magnet to poke all the way through, and then I need to remove some material from the top to place the circuit board in the correct position. I needed to create a little bracket to hold the circuit board in the right place, and the quickest way to do that was a 3D print. So I drew that up and printed it. Drilling the holes though for the bracket proved a bit interesting. Because there were small screws, M2, 2mm diameter screws, a 2mm drill simply wasn't long enough to reach down past the radius of the bearing section to where I needed the hole. So I then 3D printed myself a drilling jig which located on the centre of the hole, and then provided me with two drill guides on the back of the part to drill the holes through from the backside, and I could then tap them from the backside as well. Which solved that little problem nicely, and then I could mount the circuit board with its little bracket to the machine. So having done all of that, it works, and as I said earlier, there's still a little bit of flex in the system, but it's repeatable. So that's the key bit. I'm no longer getting a slightly variable amount of travel. It all totals up to about 50 microns, 0.05 of a millimetre, which isn't very much. And for a machine of this quality and price point, it's probably actually well within spec. I think what I need to do is actually make some parts and just see how accurately it can do it. So another mod that I just remembered about, the Spindle used to run this pulley and a different belt. So I wanted to make the spindle go faster. Generally CNC, you're running a faster spindle, carbide tools, all that kind of stuff. So I found this pulley in the McMaster car catalogue in Fusion. You just download the model, 3D model, and print it. And then, in fact, same with the belt. So I printed a pulley and a belt just to try it out, see if it worked, and it actually works really well. I mean, the belt's TPU, the pulley is just PLA. Excellent for proving the point. We'll see how long this belt lasts.